A very good afternoon to all of you. And in continuation to the previous video, I would like to demonstrate, I would like to rather derive the expression for lande-g splitting factor. Splitting factor. And in fact, what I'll try to do is I would like to develop an equation that gives us the measure of the total magnetic moment of an atom. And as you know that we have been talking about the atoms which have one electron in their first orbit. So we are treating the same kind of situation here where I have a one electron atom and I would like to calculate the total magnetic moment of this atom. And finally we will see on making some comparisons, we will have a mathematical expression for the calculation of lande-g splitting factor. Now before I proceed into before I go into the derivation of this lande-g splitting factor, rather it's more important to understand that what are the various domains of science where this splitting factor has tremendous applications. And if I start with an argument that this lande-g splitting factor has its application when we talk about electron spin resonance techniques. So in ESRs, or we also call it EPR, what happens is when you apply an external magnetic field, due to the two different orientations of the spin of the electron, you can have rise in energy with respect to the applied field in one case. At the same time, you will have the decrease in the energy of the electron, which leads to the splitting of the energy level. There is another important domain where this lande-g splitting factor plays a key role is in MRI. So MRI, what we have is magnetic resonance imaging technique. It's used worldwide to detect the problems in the human bodies. And how does MRI work is when you apply the external strong magnetic field, then the hydrogen atoms that are present in our tissues, there is splitting of the energies involved, and that splitting leads to a better topography of the tissues of the biological bodies. And this G has the calculation of G in terms of the cosmos. It certainly plays a very important role in confirming the validity of this standard model in particle physics. So rather there are many more applications that we can think about this lande-g splitting factor in almost many domains of science. So what we have is, what is our target here is that we have to calculate the total magnetic moment of an atom, and if I represent this magnetic moment by mu j, and electron will have the orbital motion, and orbital motion will give rise to the orbital magnetic moment to the electron. So for that I will have mu L, and the third thing is that the electron at the same time has spin angular momentum. So having spin angular momentum leads to a magnetic moment known as spin magnetic moment. And we better understand that if I have orbital angular momentum in this direction, the direction of the magnetic moment of this orbital angular momentum is always opposite to it. So if this is L, then mu L has to be opposite to it. If this is S, then mu S has to be opposite to it. So, so if I have L, if I treat L, this is my orbital angular momentum, and this is my spin angular momentum, and the projection, okay, so this is, say, this is my G, total angular momentum. And let me assume that the angle between J and L is, say, θ1, and the angle between J and S is θ2. Now, what we can see here is, as I said, that the direction of the magnetic moment is opposite to the angular momentum, whether it's orbital angular momentum or it's spin angular momentum. So we can immediately think about here, if I make a projection, like this, this will give me mu L, and I can think of the projection of J as mu J. So this angle is going to be θ1. So along J, I would like to take the x component of the orbital angular momentum. So when I do that, for that, this mu L is going to be equal to this mu L along J is going to give me mu L cosine of θ1. So this will be my magnetic moment along J. So taking the x component of the orbital angular momentum, the orbital magnetic moment. So similarly, we can think about, so here this θ1 is the angle between J and L, and we can also think in terms of mu S. So if you make a projection here, so here you have θ2, and you can take the x component of the magnetic moment due to the spin, that mu S will lead to mu S cosine of θ2. Now, if I write down the magnitude of the total magnetic moment in the given case, so what will I do in that case? Come on. So look at me. So what we have is, we have total magnetic moment mu J, and this is equal to mu L cosine of θ1 plus mu S cosine of θ2. So this equation will give me the measure of the magnetic moment, the measure of magnetic moment of whose component is along the J. So you are actually calculating the magnitude of the total magnetic moment with respect to J. So we have a situation like this. This is my L, and this is my S, and this is my J, and this is my θ1, and this is my θ2. Now, as we have already talked about the coupling between orbital angular momentum and the spin angular momentum, and we understand that the coupling between L and S leads to what's called as spin-orbit interaction. So what we have is, we have J equal to L plus S. And if I choose S and write down J minus L, I can do this, and let me take the dot product of this, the dot product, the self dot product. So what will I do here is, I will have S dot S equals, J minus L. So this is This is J minus L dot J minus L. Okay, so we'll get here S square equal to J square plus L square. This is minus 2JL cos theta. So we can see from here, we can calculate this is 2JL cosine theta will be equal to S square. No, let me keep it there. So J square is there plus L square is there. I'll transfer this on the other side. This will become minus S square. So this is not theta, this is theta 1, because we know that this theta 1 is between J and L. So in proceeding from here, what we will have is we will have cosine of theta 1 will be equal to J square plus L square minus S square divided by twice JL. Sorry. Okay, so this is the measure of the cos theta 1. Okay, as we know that we have that equation where we calculate the total magnetic moment. So in calculating the total magnetic moment of this one electron atom, you have to calculate cos theta 1. Cos theta 1 is calculated. Now we want to calculate cos theta 2. So obviously I would like to moderate the coupling equation in such a way where I will have the dot product between J and S. So that should be the case. So for that purpose, what I will do is J is L plus S. So I will have L equal to J minus S. So L equal to J minus S will be a right choice here. So J equal to L plus S. That implies L equals J minus S. Now take the dot product, so I will have L dot L, then I'll have J minus S and dot of J minus S. So we will have here L square equal to J square plus S square minus twice JS cosine of, now I have the angle theta 2 here. So this will be cos theta 2. So from this equation I can calculate this cos theta 2. So this cos theta 2 is going to be J square plus S square then minus L square divided by 2JS. So what we have done, we have calculated cos theta 1, we have calculated cos theta 2, and we can include these expressions in our original equation. So what was our original equation? It was mu J is mu L cosine of theta 1 plus mu S cosine of theta 2. So what will be mu J? Mu J will be mu L times cosine of theta 1. Cosine of theta 1. What was that? That is J square plus L square minus S square. This is J square plus L square minus S square divided by 2. This is the problem of the board. It's 2JL. Okay. 2JL. I'll close it. Then I'll have plus mu S times j squared plus s squared minus l squared. This is j squared plus s squared minus l squared divided by 2js. Divide by 2js. Okay, this is it. Okay, now what we have, we actually know these angular momenta. We know the relation between the total angular momenta of the electron and the corresponding quantum numbers, and for orbital angular momentum, for spin angular momentum, and for the total angular momentum of the electron by solving the problem of hydrogen atom in spherical polar coordinates. So we understand from that this j squared is j times j plus 1 h bar. Okay, where this j is it's the inner quantum number, it's the total quantum number. And similarly for L squared, what we have L times L plus 1 times h bar, and for S, for spin angular momentum, the magnitude of spin angular momentum, we have S squared is S times S plus 1 h bar. So what we can do is we can substitute all of these values in our equation, because what we are trying to do is we are trying to calculate the magnetic moment, the total magnetic moment of this one electron atom. So let's do that. What we will have mu j is mu L times. Okay, so you will have j times j plus 1. It will have h bar as a multiplier, then plus L and minus S. Then you'll have plus L times L plus 1, and then you will have minus S times S plus 1. And all of them have h bar as a multiplier. Divide by, yeah, it's 2jl, so this is 2 times, this is 2j times j plus 1. You have to have under root here, h bar. And I think here it has to be squared because you have under root. Here, what you have is, in actuality, you have j equal to under root of L times L plus 1 h bar. So if you take the squaring, then this j squared will be L times, sorry, j times j plus 1. It will be j times j plus 1 h bar squared. So in every case you will have h bar squared, and h bar squared. So that's why what we are going to do here is we are going to put h bar squared over here, and you have j, then for j, after j you have L. So for L you will be using under root of L into L plus 1, and it will have its own h bar. This h bar and h bar squared will cancel. Then you will have plus mu s times. So now we'll come here. So for j, s and L, we are going to make the same kind of substitutions. It is j. So for j, I will be using j times j plus 1. Then for plus s times s plus 1. And then minus L times L plus 1. And obviously you will have h bar squared as a multiplier. Divide by 2js. So this is 2 under root of j times j plus 1. And it has its own h bar, then under root of s times s plus 1 h bar. So again, here we can see this h bar squared will cancel with h bar squared. All right. So this is the situation till now, and we are moving on. Let's see where we will end up. Okay, so what we have this whole thing, and we have another important thing here is mu L, and again here we have mu S. Now we understand the value of mu L, the relation between the magnetic moment due to orbital motion of the electron and the orbital angular momentum. It's like GL E by 2m L. And similarly for mu S, we have GS 2 times E by 2m S. And we can extend this to GL and E by 2m L. So this is E by 2m. So for L, what we have under root of L times L plus 1 H bar. And the same thing will happen here. You will have GS E by 2m under root of S times S plus 1 H bar. So for the time being, I'll not be using GL and GS. So I treat my magnetic moment, orbital magnetic moment, and this must be equal to this whole thing, and the spin magnetic moment must be equal to this whole thing. So we understand that this 2 is because of the 2 spin states of an electron. That's why you have a 2 multiplier for calculating the spin magnetic moment of this electron. So now let's go back to that equation. So if I go back to this equation, what I will have is here, instead of mu L, I will be using E by 2m, then under root of L into L plus 1 and times H bar. This will be one thing. And here, okay, and here for mu S, I'm taking the magnitude only. So for mu S, I'll be using 2, and then you will have E by 2m, and then you will have S times S plus 1 H bar. Okay, so this is the kind of thing. So what we have here is E H bar. Now you can see that this is E H bar by 2m. This E H bar by 2m is nothing but Bohr magnetron. Bohr magnetron, mu B. So instead of this EH bar by 2m, I can use mu B. And here we can see this under root of L times L plus 1 is going to cancel with under root of L into L plus 1. And spin S into S plus 1, it's going to cancel with S into S plus 1. So what we are left with here, it's right down that. So what I have mu J is mu B times. Now I have mu J is mu B times, this is J times J plus 1, then L times L plus 1, plus L times L plus 1 minus S times S plus 1, divide by 2J times J plus 1, okay? And then we have plus, okay, we have 2 mu B now, because here we have 2 times Bohr magnetron, so this is 2 mu b times, okay, so this is plus 2 mu b times, yeah, j times j plus 1 plus s times s plus 1, then minus L times L plus 1 divided by 2j times j plus 1. Right? So this is the measure of the total magnetic moment of this atom, and we can further move on from here. You can see that here we have 2 times mu b, so mu b can be out, and the denominators are the same. The denominators are same. This is 2j times j plus 1. This is again 2j times j plus 1. So when we do that, I'm going to write down this mu j. Mu j will be mu b. I will have a single bracket, and here I will have 2j times j plus 1. Alright, that's fine. So now we can see from here, come on, this is 2 times j plus 1. This is j times j plus 1. It will become 3j times j plus 1. So this is becoming 3j times j plus 1. Okay, now move on back here. Now let's look for s term. So for s, you have 2 times s plus 1, and s times s plus 1, it will give us 1 s times s plus 1, and the sign will be plus. So I will be writing here plus s times s plus 1, and after this we have the last term, that is L. So here we have minus 2L times L plus 1, because this whole thing is multiplied by 2. So this is minus 2L times L plus 1 plus L times L plus 1 will give us minus L. It will give us minus L times L plus 1. Alright. This is it. So mu j will be mu b. I can think of writing it like this. This is 2j times j plus 1 divided by 2j times j plus 1, and then 2 plus j times j plus 1, because this, when added with this, will give us 3j times j plus 1 plus s times s plus 1 minus L times L plus 1. This is also divided by 2j times j plus 1. Alright, so we can see this and this will cancel, and we'll get 1 here. So what we will have mu j. Mu j is equal to mu b, and inside I will have 1 plus j times j plus 1. Then I will have plus s times s plus 1. Then I will have minus L times L plus 1. And in the denominator I will have 2j times j plus 1. Alright. So we can make a comparison here. So if I write down mu j is g j mu b. Okay, so we already have a relation between mu j and mu b, and in between there is g, what's called as lande-g splitting factor. So this equation is giving us the measure of the total magnetic moment of this atom. And if I compare this equation with this equation, I will be obtaining this g, and this g was our target. So what is g? G is the bracketed term. So you can calculate the bracketed term to measure the splitting. You can measure the splitting of spectral lines by calculating the G. So what will be this lande-g splitting factor equal to? This G will be 1 plus J times J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2J times J plus 1. So this was our target. We wanted to obtain the expression for lande-g splitting factor, and this is my expression for lande-g splitting factor. I think I have already talked to you about the application of calculating this magical number, because it gives us the measure of the splitting of the spectral lines. Okay, bye.